Antoine Lavoisier, he played a big role in the French Revolution. He was a scientist, and before he got executed by the Reign of Terror in the French Revolution, because he was associated with the family of tax collectors. And in the Reign of Terror, they gathered all the nobles who were responsible for collecting taxes, yeah, and chopped off their heads. But before he got his head chopped off, he was a very important scientist, and he made some major accomplishments. But the main idea is that he did now start pushing forward from the Alexandrians. So until this point, the science of chemistry and gases and so on was basically stuck for 2,000 years. Now what Lavoisier did was he broke down the elements of antiquity, which means earth, air, water, fire, ether. Well, ether he didn't break down, but earth, air, water, fire, he broke them down. What that meant was that he said, baloney, these are not elements. Right? So how he did that was, again, using the same techniques that the Alexandrians had developed, namely careful observations and measurements. You know, like Eratosthenes observing the shadow and measuring the angles and measuring the distances. Careful observations and measurements, same techniques, and measuring weights and volumes, just as Archimedes did, measure weights and volumes. And so his first experiment showed that air is not an element. And I'm going to make a demonstration of that. So I have here, I'm going to actually demonstrate two things by this experiment. I'm going to demonstrate that hot air expands and therefore escapes. I'm going to repeat the experiment of Philo. But I'm also going to show you that air is not an element by the same experiment. So here I have a candle, and you know that in order for the candle to stay lit, I need to first of all light it, right? And for the candle to stay lit, it needs air, right? And for you guys to stay alive, you need air. Take away your air, you die, right? You take away the air from the candle, and it extinguishes, right? So now in this container, I have air, right? So I'm going to take away, or not take away, but I'm going to cover this flame with the candle and hold it there, all right? And you should watch what happens. It's difficult to see very well, but if you look closely, okay, I can lift this up a little bit so you can see it better. If you notice the level of the water, okay, underneath has actually risen up, okay? So what happened was two things. One is that the candle extinguished, even though when I did not cover this, the candle kept burning and burning, right? So what I did was I gave it a fixed amount of air, and the candle burnt and then stopped burning. Okay? The other thing that happened was that the amount of air in here is now less, okay? Now, there's two reasons why the amount of air in here is less, and one of them is the main reason. The main reason is that the candle heated this air, and the heated air escaped from the water, and so when things cooled down, I had less air, and the water rushed up to fill that volume. Now, it didn't rush up all the way, because there's still some air left in here, okay? There's still some air left in here. However, the candle extinguished. So if there's still air left in here, why did the candle go out? Okay, this is now Lavoisier, okay? He says, aha, the reason that the candle went out, even though there's still air there, is because air has two parts to it. There is what he calls the combustible part, the part that supports the burning of the candle, or combustion, and there is the non-combustible part. Air cannot be an element because the gas which supports combustion is gone, the candle ate it up, okay? And the gas that did not support combustion stays there. And so air cannot be an element because it consists of two things. When something consists of two things, it cannot be elementary, right? That's the idea. So air, he says, this is his conclusion, and he made the names. These names were given by Lavoisier. Air, he said, consists of oxygen, which supports combustion, and nitrogen, which does not support combustion. So what I'm going to do is I'm going to take the nitrogen in this air, and I'm going to cool it down, And I'm going to collect only nitrogen for you, which is difficult to do when you have such a big chamber, right? So since I come from a laboratory of low temperature physics, okay, I can take some refrigerator, really powerful refrigerator, and cool down the air, and then pour the cold air. I have to put it down here. Let me put it over here so I don't break my computer. I'm going to pour the cold air into this cup. Okay? And this cup now has in it a liquid, okay? This liquid here. Okay? And that liquid is very, very cold, okay? It's it's cold enough that the air in it is liquefied. But I'm telling you now, it's not the air that's liquefied. This is not liquefied air. This is liquefied nitrogen. Okay? So what I'm going to do now is I'm going to do an experiment for you. But first I'm going to ask you a question. That what if I take a match, right, and throw it in there? What's going to happen? So, have I done? No. Okay, everybody close your ears. Duck, hide. All right. In fact, here's something interesting. Let me take this thing here and not actually put it in the liquid nitrogen, but kind of hold it up here. Why did it go out? I didn't put it in the liquid. Why did it go out?
Smoke.
But what's the smoke? What is the smoke?
That's still liquid nitrogen.
Nitrogen gas, right? And what does nitrogen do? It does not support combustion. So this is nitrogen. So now I've separated in front of you. I separated the oxygen and the air from the nitrogen. This stuff up here is nitrogen. Okay. This stuff here is liquid nitrogen, which has some rather interesting properties when it's cold. Okay. Here's some liquid nitrogen. I'm not allowed to smoke in this course, but I can later on come and have some Doritos. They might be all gone. Now, be careful not to get this on your clothes, okay? Because if you get on your clothes, you will definitely get frostbite. This is the advantage of sitting in front.
No.
I'll give it to you.
My hands went numb. I don't want to.
Anybody want some frozen Doritos to smoke? Anybody like smoke in class? No. Now, the liquid is very cold. However, I can still pour it in my hand and not burn. I shouldn't pour it on my clothes. On my clothes, it will freeze the cloth and burn my skin. Okay, that'll be frostbite. But in my hand, it evaporates instantly because the temperature here is, if you know the absolute scale of temperature, room temperature is about 300 absolute Kelvin, and this is about 80 Kelvin. So that means that this temperature here is 300 minus 80 if you want to use the centigrade scale. So it's minus 220 degrees centigrade. Minus 220, okay? Colder than the coldest places on Earth. Okay, so the reason I can put my hand in here for short periods of time is that the nitrogen boils and surrounds my finger and makes a nice insulating blanket around my finger for a short time, okay? Now, there's a professor over here, his name is Bob Richardson, who actually drinks the liquid nitrogen and throws it out fast enough, okay? But you see, he already has a Nobel Prize, and I don't want to do it. So he's done his thing. Okay. So there will be some liquid nitrogen left, and you can play around with it. Another fascinating aspect of liquid nitrogen is that it changes the properties of objects. For example, this object here is a plastic tube called Tygon, and it's very flexible at room temperature. And I can cool it down in liquid nitrogen. Okay, you can see the one part of. Oh, I should have done this first. Okay, if I take I can cool it down in liquid nitrogen. Okay, you can see the one part of. Oh, I should have done this first. Okay, if I take this tube of Tygon, right, and I smack it against the table, nothing, right? It's plastic. It's completely flexible. See, so I can take now this tube of Tygon and cool it down. Let me actually put some more liquid in it so that a significant part of the tube cools down, and I have to kind of wait till it's really cold. And then, okay, it's really cold. I go, oops, not cold enough. Okay, gotta wait for it. Maybe I try the big one. Try the big one. We're going to have to erase that from the video. All right, there's my liquid nitrogen. I want to make sure. You kind of have to wait till it's fully cold. All right, let's give it a try. See that? It's broken like glass. Shatters like glass, okay? So people do this with a banana or a rose petal, something to make the rose petal shatter. So once you cool things down to really low temperatures, you can get all kinds of wonderful properties. Like if you got a wart, you can cool it down with liquid nitrogen and a Q-tip, then just pull the wart right off your skin. Okay? The wart has no nerve endings, so it won't hurt. But don't cool your skin with it. All right, so that was just a little bit of fun with Lavoisier's nitrogen. So here he explained that that air is not an element. Now his next experiment was to show that earth is not an element. So he tried all kinds of different ores and rocks and stuff. And basically what he tried to do was he tried to heat them up to see if they would separate out into different elements. And what he found was that if he took this particular red oxide, it looks like earth, you know, like covers the soil, call it mercuric oxide. If you take this red oxide and you heat it up, it actually separates into mercury, okay, the element mercury that you have in your thermometers, and the gas oxygen. And he collected this gas oxygen, okay, and he weighed the mercury and he weighed the oxygen, and he proved that the weight of the mercury plus the weight of the oxygen together was equal to the weight of the mercuric oxide that he decomposed. So here you have something that looks like earth, or that somebody would normally call earth, would break down into two other objects, which are mercury and the gas by oxygen. And since the weight of these two sums up to the original weight, this cannot be an element. So earth cannot be an element. These might be elements. Okay? This is a picture of Lavoisier doing this experiment of heating up mercuric oxide and collecting the oxygen. And that's his wife, I forget her name. She helped him with all these experiments and took wonderful notes, which still exist, of course. Now, he came to the next element, which is water. And he proved that water is not an element because water can be broken down into hydrogen and oxygen. But you know, by his time, he already had hydrogen, which was called the flammable gas, and he just discovered oxygen. So what he did was he combined, okay, for example, hydrogen can be obtained when a metal reacts with an acid. This is something that Maria Prophetissa probably knew about. Okay? So he collected the hydrogen and he collected the oxygen from one of his experiments, like burning up mercuric oxide, and he combined these two in a sealed glass container, and he lit that with a match, and there was a nice pop, an explosion. And after the explosion, the walls of his flask were covered with a colorless liquid, which he then tasted and tried it out, and he found that the colorless liquid is really water. Okay? So what he showed was that hydrogen and oxygen together, when lit with a match, combined to form water. And so Lavoisier identified the liquid as water.
We're going to mix now the oxygen with the hydrogen all in one balloon.
Oh, okay.
Okay, and that's what I have in this guy.
All right, that balloon looks larger.
Well,
slightly larger.
It's larger because here's what we have to do. I'm going to make a bunch of bubbles in this tray of soapy water.
Okay.
You are going to then scoop up those bubbles right off the top, get as many as you can, leave the water behind,
Okay.
and then we'll just add a little flame to it.
Oh, all right, so you're going to blow me up, in theory.
Now, this could be a little bit louder than the previous balloon, so why don't you go ahead and put the earmuffs on right now.
Oh, you were just
We'll get
making
ready
me
for
look
it.
all kinds of beautiful this morning. Okay.
Now, I'm sure you can still hear me. Now, in order to pick up the bubbles, you're going to have to get your hands wet.
Okay.
So dip your hands down in the soapy
You've
water.
told me to take off my rings already.
All the way up to about right there.
Okay.
Perfect. Perfect.
So now what?
So now go ahead and take your hands out.
Okay.
I'm going to make some bubbles in here, and these bubbles are filled with a mixture of hydrogen and oxygen gas.
All right.
We're going to see what happens if we add a little energy to that from the flame of a match
Okay.
while they're in the palm of your hands.
Alrighty.
So what I want you to do here in just a second is scoop up as many of those bubbles as you can. Just skim them off the top.
I'm getting nervous.
Leave the water behind.
Okay.
Perfect. Yeah, that's nice.
Okay.
Okay, extend your hands out in front of you. Put your hands flat.
Okay.
And for
you
everybody else
later.
in the studio, you might want to plug your ears because in 3, 2, 1. You okay? Yeah. You had a lot of bubbles there. That was and
Now his compatriot in England, it turns out Priestley, his name was, his experiment was even better than Lavoisier's experiment. Priestley broke down water into hydrogen and oxygen and collected the two. Okay? Collected hydrogen and oxygen. But the way he broke it down was extremely clever and extremely telling about the nature of matter. He decomposed water by using electricity. So I'm going to do that for you. I'm going to decompose water with electricity. So over here, I have a jar of water, right? And in it, I have two, for those people who can see it with the naked eye, I have two electrodes. I have two cylinders, okay? They're made out of stainless steel. And one of these cylinders is connected to a terminal of a battery, just like Priestley's. And the other one is connected to the other terminal of the battery, but I haven't made the connection yet, okay? There's a little bit of gas coming out because the metal is reacting with the water in there. I actually have primed the water a little bit to carry electricity by putting a little tiny bit of sulfuric acid in it, okay? That's why you can see now that the metal and the sulfuric acid are reacting to generate a little bit of gas. I don't know if you guys can see the gas, but those people who are close up can probably see little gas bubbles on the cylinder. But that's not so interesting as if I now close this battery and I watch the two electrodes for a little while. You probably see this much faster than anybody else. And you will see quite a lot of activity in this area, and you'll see bubbles forming at each one of these electrodes. This is my laser pointer. Okay, do you guys see the bubbles forming here? You see these bubbles forming and then taking off here? See that bubble? See that bubble there? So these bubbles are bubbles of hydrogen and oxygen. Okay, I'm not going to collect them because it's dangerous, right? Because the hydrogen will combine with the oxygen in the air and go pop. If you come up over here, you'll see that the evolution of the gas is rather dramatic. If you look directly at the apparatus over there, you can see the gas coming out. That's hydrogen and oxygen coming out. So that's how you can make hydrogen and oxygen in today's technology. Okay. So both Priestley and Lavoisier showed that water is not an element because it can be broken down into two other elements, which is hydrogen and oxygen. And you all know the applications for hydrogen. I already talked about it. We can use it to fly, okay? Except you got to be really careful with hydrogen. You know, there was a very famous incident that in Germany they really had cross-Atlantic transportation with dirigibles filled with hydrogen, and then they had this nasty accident. Does anybody know where this accident took place? New Jersey, right? So this Hindenburg, very famous ship, had arrived, and there was some spark or something, and the spark blew up the hydrogen. From then on, people didn't use hydrogen to fly. Okay. Now, just like Archimedes, okay, Lavoisier was very introspective. Okay? And he wondered, he had found these elements, oxygen and nitrogen and hydrogen, and he really wondered, are these chemical elements really elementary? And it's amazing how he thinks, and he says, nothing gives us the certainty that the substances which we now believe to be simple, namely elements, are actually simple. This stuff presents today merely the limits of our analytical chemistry, of our approach to understanding matter. It cannot be further decomposed with our present knowledge and devices. So these elements cannot be further decomposed.